This is Introduction to Quantum Computing, week number 4. So far we've talked about qubits, how we can manipulate these qubits, which are two-dimensional complex vectors, using Dirac notation, and how we change the state of the qubit using these unitary matrices or gates. Then we talked about how to combine them with the tensor product, and in particular we saw that as we add qubits together, the dimension of the complex vector space grows exponentially. So I need an exponentially growing amount of information for one coefficient for each basis vector to specify the state of a n qubit system. Now, there's a reason that there's a picture of a dog here on the screen, and that's because I want to talk about compression and the question of how or if we can use quantum systems to achieve some sort of compression in representing data. So naively you might think, well, I could store an exponential or even more amount of information in qubits because the size of the space grows exponentially. Now you'll notice something about this picture. It's not such good quality, I mean, depending on the quality of the stream you're watching this on. This image is the original image. It's 894 pixels wide by 722 pixels high, and it is a 300 kilobyte file. The original one I had on the screen is still 894 pixels wide, 722 pixels tall, but requires only 30 kilobytes of data. That's a factor of 10 reduction. And by eye, maybe you didn't even initially notice that there were some discrepancies. So if I flip back and forth, you can definitely tell that there are some differences, but you still recognize this as a dog. If it was your dog, you would probably recognize it as your dog very easily. It's not my dog. Now, this kind of compression is called lossy compression because this new image that I obtained from the original image has information that's been lost. It can't be retrieved. I can't take this image and get back to this image by decompressing the JPEG file. So the JPEG algorithm is a type of image compression algorithm that reduces the file size but at the expense of losing information. The kind of information compression that we want to talk about is lossless data compression, and that's more relevant if you're thinking about something like zip files that you might download. So you certainly don't want to download a zip file and it only work 75% of the time, or it only decompress 75% of the files that you zipped up. So as a quick demonstration of that, I found an online tool that will demonstrate lossless compression. I'm going to type in a sentence here. I have 4 qubits. I have 4 qubits. Let's name them qubit 1, qubit 2. This isn't what I name my children, but maybe. And qubit 4. The kind of compression that's done by the zip algorithm is deflate. So if I click compress, what I find is I've taken a 70 byte file. This text file would require 70 bytes of data, and I end up with a 53 byte file, a zip file instead of a text file, and that is a compression ratio of 132%. So that's pretty impressive. I took this text file and reduced it by 132%, and I haven't lost any information whatsoever. How can that be done? Well, you can see that Google has helpfully underlined these words that it doesn't know. Qubit, which has been repeated 1, 2, 3, 4, 5 times. So I can represent that 5-character symbol by something that requires less data, and then have a lookup table that points to the one instance of that long repeated word. Now, lossless compression really only works if I have some repetition. So I've found a random string, maybe it's my password, who knows? Probably a strong password. Not anymore though. And if I attempt to compress this, you see that actually I've increased the size of the zip file. So it's really only the repetition that allows something like lossless data compression to work. If there's no repetition, then any compression algorithm is likely going to fail, in the sense that it's going to actually produce a file size that's bigger than the original file size. So if I have a completely random string of letters, there's just no way to compress it. Okay? All right. So now we're going to ask the question, what about qubits? These, I'm trying to compress bits with bits. What if I use qubits? What's the intuition for this kind of question that's been asked? So I recall that if I have a qubit, it can be represented as a linear combination of the basis elements 0 and 1. And we also saw that this can be written in our block sphere representation, so a different set of variables. So let's just do a change of variable here to theta and phi. Okay, and now you might say, well, let's take this angle for example, and let's take that random string and turn it into bits, and just let theta be the binary expansion of this random string. Yeah, that looks pretty random. What do you think? And the 70 bytes, so I need 70 times 8 bits in this decimal expansion, but I could do it. I can put an infinite number of decimal places inside of this theta. So it seems like I can encode, in fact, an arbitrary amount of information into a qubit by just putting it as the binary expansion of this angle theta. But here's the problem. If I have this state and I want to read the data, remember that what comes out is only ever 0 or 1. Of course, that's related to the probability. So there's some probability of seeing 0 or 1, and that's related to theta. So certainly the probability of seeing one of these outcomes is dependent on theta, and that means that maybe I can get some information about this data that's been encoded. But again, there's only 2 different outcomes. So in fact, the most information I can get is 1 bit, because I can only distinguish one of 2 possibilities. So regardless of how many bits I try to encode in a qubit, I can only ever get out 1 bit of information. And if you're interested, this is called Alevo's theorem, and the proof is beyond the scope of this subject, but I think the intuition with measurement is sufficient. If I have more than 1 qubit, so I can have like an arbitrary dimension system. So I have a system and I can define it by some basis, B1, B0, B1, B2, and all the way up to, say, BD, where D here is the dimension. So the dimension of a vector space is the same as the number of basis vectors I can find for it. If I have some vector that it exists in this complex vector space that's spanned by this basis set, and I perform a measurement, I try to read the data, then what comes out is one of these basis vectors. And if I have elementary systems like qubits, there's an exponential number of basis vectors, but, so in this case I've chosen D. However, to distinguish one of D possibilities only requires log 2 D bits of information. So even if I increase the number of qubits, I'm not increasing the amount of information I can store and retrieve from those qubits exponentially. I am only increasing it linearly at the number of qubits. N qubits, n bits of information can be accessed. This is called Alevo's theorem, but the theme of this week is no-go theorem, so let's call it the no exponential information theorem. So next, we're going to see that it gets even worse, and there are some other things that we can't do with quantum information.